Everybody, welcome back. Thanks for coming. Recording's on, so all the conversations, all of this is known.
Yes. I'm definitely never going to infringe against Nintendo. Put that on record.
What?
I didn't hear that. I don't know what you're talking about.
Yeah.
A couple things to start off class. Number one, thanks for doing the formative assessment. Everybody knows what a Q matrix is, it looks like. That's pretty clear. Check. Number two, I have your homeworks. I haven't graded them yet. How'd that go? How'd Argon go for you? Painful?
Yes.
Do you struggle?
Yes.
We had a study session yesterday.
The struggle is the point. Struggle is the point. But everybody seemed to be successful, right? More or less?
Yeah, I was just thrown off by the directions because it asked you to upload the Argon output file, which if it was correct,
Had nothing.
and
Yes.
you can't upload an empty file.
Which I never knew about this anyway, which is silly because a 0 kilobyte file could exist. But so interesting on that. When you called Argon, you used what at the very end, the very bottom? What command did you use to invoke R to run a script file? Can you please shut the door? Oh, thank you. Oh, sorry. Thank you. No problem. What?
Our script.
R script. Did you use R script? Or what did my instructions have?
Well,
Yes.
What? Aptainer, but yes, Aptainer just invokes the Aptainer instance. At the end of the line is the command that calls R. So the first part, Aptainer. Should I pull up an example? Should I show it? Okay, I'm just going to do it in the terminal. I'm using SSH. By the way, if you have SSH, you can create credentials in SSH that remember a lot of your passwords or connections, so you don't have to type as much. I'm glad, Sergio, you mentioned that. So let me just go through this again. So think about what we're doing here, right? Argon's where we need to execute our stuff. But to get to Argon, you had to go through notebooks, most of you, right? Not just SSH. You could use SSH. So you log into one computing system, notebooks. And then you use it to log into Argon. And then guess what Aptainer is?
Another system.
A third, although it's running on Argon. But it doesn't know that it's running on Argon. It's sort of the simulation theory version of our universe. All right? Like if you created a container of life and didn't tell anybody it was just a container. Anyway, sorry, too much. So here, the reason why I ask what did you use before to do that, I want to show this to you. So here I'm in Argon, so forget the notebooks, there's no notebooks going on. But here, if I look at, this is the very first file I did, it didn't have Aptainer. I could change this to look like Aptainer by just a few commands, right? I could do, whoops, what the heck just happened? Let's try this again. Okay, to get Aptainer working, I can just modify this really quickly to look like this. Aptainer, the location of my Aptainer image. That's right, and the word run. So let me dissect this real quick. Aptainer run means start this miniature computing system within Argon. That's all this first part does. And then the last part, after you get part of this image file, right? After you get past the image file, sorry, rather than pointing to it, how about I highlight it? Right? So all this does is says, hey, I'm going to create this miniature virtual computing environment called Aptainer. It's going to run whatever I told it in there, okay? But this last part is the same command that you'd run on Argon to run R. You can actually run that on your own computers. Nathan said he ran R script. This one is rcmd batch. They're different, but they're not. They still execute R. But if you run rcmd batch, you get an R out file where it dumps all of the output from R. Right? If you run R script, you do not get an R out file, right? So when you don't get an R out file, the .o file that's empty when you run rcmd batch exists, and it contains all the output.
Okay.
All right. So R is like writing stuff to the screen, or it's got like this standard output, right? It's trying to figure out, it's sending messages somewhere, and how you call it and what you connect to it determines where those messages go. Since we're running it with this command line interface, it doesn't have a screen to send those messages to, so it starts to dump them into a file. It doesn't know where that file goes, and if you use R script, then it doesn't even go anywhere. It goes to null unless the system captures it, and that's what the output file does. Good question.
So sorry, but you're so thank you.
There we go. Okay, so there's a difference. rcmd batch I used here just to show you it. It has an R out file. That's useful. R script has a different use. Have you ever heard of command line arguments before? Anybody else? Okay, so in a command line argument, it's like Control X here. So if I want to do obtainer, I could do okay, so this is an obtainer call. All right, so the first word is the program that's going to run. Everything after that's called an argument to it. So when Argon starts to run this, it says, oh, I'm going to run the obtainer program. All right, so it starts this program, and it sends to obtainer these instructions. Those are called arguments. The same thing happens if you write a function. The input into the function is often called an argument. In a command line, it's not a functional form, but everything that shows up afterwards is an argument of some sort. So for instance, what this will do is create my miniature virtual world named obtainer, right? I'm in Linux in obtainer right here, such that if I type my current working directory, oh, it takes the working directory, I totally forgot that. Anyway, so I'm in my obtainer world, but basically it sends arguments. In R, if you're using R to do simulation studies, which I'm guessing many of you will do, right? Simulation studies have replications, and replications need replication numbers. So we need a way to pass replication numbers to R from Argon, because Argon is going to basically schedule it. If you set it up to run an Argon, you can set one file and run 100,000 analyses from it. They'll each have a number, 1 through 100,000. How do you get that number out of Argon and into R? That's where R script comes in. The scheduler in Argon, you see here's this R script command. Here's the R file, that's one of the arguments. This thing right here is a variable that Argon creates that says which task ID specific to this job it is. So which replication. So you can actually input, but R script allows you within R to capture that, to get which replication number it is, because that replication number often will contain things in it like what simulation conditions you have, how to write files, where to write those files, what to do, right? So the difference between R script and rcmd batch, I'm down the rabbit hole here a little bit, but I wanted to give you this impression because you use rcmd batch if you want to have a nice output file. You use R script if you want to send R command line arguments. How's that sound?
So that creates a variable within IRT simulation rep.r that has that before it runs the R code.
If you code your R file right, yes. So let me show you that. So in this R simulation rep, let me go back a level here. Here's my IRT simulation rep. There's a command in R called command args, which will capture that input. So I take the command line argument, I save it, I make it a number because it all comes as characters, character variable, make it a number, and then I do stuff with it. So that If you're interested in all this, I don't know if Ariel will cover this in his simulation class. When I teach simulation and stuff like that, that's how to get Argon to work for you. Because you can easily run an Argon command, the command, you know, that Q sub command that you're all familiar with now? There's an option with it. Another command line argument, this -t, and then you have a start number to an end number. This is the beginning replication, this is the end replication for a simulation. So you can do multiple replications of the same thing all at once. So, difference between R script, RCMD batch. R script gives you command line arguments, good for simulations. RCMD batch gives you a nice output file, good for single analyses. That's how I look at it. Anybody have better details than any of those?
I did it slightly different.
Yeah, what'd you do?
So I redirected the output to, so I did our script and then,
Yes, you can do that. You can add an argument to R script to tell it where to output to.
and I also, the obtainer, I made, it was a sandbox version, so you can, because there was some read-only permission issues, so
In my obtainer? Shouldn't be.
It might have been.
I've had other people. Anybody else recreate an obtainer image or use mine? And it worked, right? Yeah. There's an issue in mine in where it wants to put your R libraries. Many of you encountered that. Are you familiar with this? It's the big struggle on network computing is you can't put things where you don't have permission to put them there. It's kind of like life too, right? You're moving, you got a bunch of stuff you need to stash somewhere, you stick it on like the corner over here, it's probably not going to go well, right? So the way that I've kind of come around to fix it is to, in the library command, you can actually give the path to where it is. Here's the problem. There is a way that you can create that path so that R always knows it. But that's going to be a little bit different for each one of your logins for Argon, and I'm not sure how Aptainer interfaces with it. So I didn't teach you that. So for most of what we're going to do in this class, just add what that where you install the package with the library path, put that on the library path line too. When you call a library, there's an option called lib.loc that will load it. So sorry about that. Yeah.
What kind of output file is the result of the R script option?
By default, none. Yeah, so you can run R script and see nothing. It will write output. R script will write output to the screen by default. So, what do I mean by that? You want me to show a small example?
Yes, please.
Okay. I go back to my main, make a directory, example. I'm going to make an R file. I'm going to call it example.r. Okay. All this file is going to do is take in this command line arguments. Okay. So here, whoops. Man, I did it wrong. You can tell this is not like my field of study, but if I do this, args equals command args, and I do trailing, was it trailing only? Well, you know what, I'm just going to print them all out here. And then print args. So if I ran this in R, in my like R Studio or whatever, when I run print, it just, to the console, it just displays things, right? So if I run this now, and I say, let's see, do I have R running? Yes, I do. Okay. I say R script example.r hello Vladimir. It is now going to print to the screen that print command. So I have all this stuff here, and that last one, that args at the end here, that's the command line argument I sent it. Okay? But if you look in the contents of my folder, all I have is example.r. I don't have an output file. So its default output is the screen. Okay? Our CMD batch of example.r, hello, Vladimir, will run, and you see nothing.
Yeah, because we have an output file, right?
But now, so here's the other funny thing. The command line argument, hello Vladimir, is now my output file. So if I do, you'll see the R output altogether. This, if I didn't give it a command line argument though, it would not write. It would write to the R out. In fact, if you look, it did not save the hello Vladimir on the argument itself. So there's no inputting of command line in our CMD batch. So I have to take this off, rerun it, and now I look and there's that R out file. Does that answer your question?
Yes. Follow-up question. So
Yes.
we have those results on the screen. How can we store them or work with them?
Good question. So if they're on the screen, like right up here,
Yeah.
from our script, what you end up doing, particularly when Argon's scheduler runs it, like when it runs, when you do Q sub, right? If I did, I don't have a job file, but if I Q sub this and send it to the scheduler, there is no screen. It does not write to it. That's where it writes to the output file that ends in an O. Okay? Everything that would be written to the screen ends up in that output file.
Great. Okay.
Okay.
Great. Yes.
Great.
Thank you.
Thank you. Other questions? Yeah.
I guess the follow-up to that would then be, how would you use that output file? You said there's no set format, it's just saved in that file.
So, you don't. What I do with R, and actually this is a mirror of what this high throughput example is. I didn't share this with the class. What I'll do is build R data files, the R data, and save whatever I need to save in an R data file from that replication. And then with another script, I go and process the results. So everything I might need to use in an analysis somewhere, I just save as a file. And if I'm not sure, I use the lazy way. Ever use the command save.image in R? It saves the entire global environment to a file. So if you don't know what to do, if like you want to save it all, save.image is an easy way to do that. Although CMD stan objects are a little bit flighty with that. You can't get the full. You have to sort of get the draws and get the summary out to do it. But that's how I will do it. I will not process output files to save my life. That's what you have to do with M+, and I'm not going to do that. So, other question?
Yeah, so the way I've done simulations in the past
Mhm.
is I have created a script that will generate, say, 100 data sets.
Yep.
And I'll just run it, takes 20, 30 seconds and stuff. Then I'll create a batch file that will reiterate running the script through each iteration. And so can you show us how I'd ask Argon to just run like 100 R files or 100 M+ files?
Yes and no. Yes and no. That's sort of outside of where we're going to go with the class.
Okay.
I'd be happy to share with, like, if we have a meeting, or if you all at GMAS want me to give or Nathan can give it, the demo with Argon, if it makes a difference, yes. I'd be happy to talk to you about it I apologize, everybody. If everybody wants to know, I will, but just I got a class to cover. The key in thinking of Argon is thinking this: the queue that you run your job on. The all queue is fantastic. It's also like living dangerously, right? It's fantastic because you can get 80 things running all at once, which is awesome. Like, oh my goodness, my simulation is halfway done. It's living dangerously because if Jonathan Templin decides to use his resources and your simulation is running on it, which you won't know, it ends immediately. So planning that means the goal in planning your Argon script is to think about where the bottlenecks will be with computation and to build a script that sort of addresses those. So if there's not a lot of computation time, like you have 100 files, you generate 100 data sets, what I would do is write a single replication file that generated a single data set, did a single analysis, and saved those results. And then I would call Argon with it, with that command -t, 1 through 100. That's how I would do that. If you have a different method where you have one data set and 5 analyses, it's a little more complicated. I'd probably generate the data sets first, and then create the Argon files to know where to find them, if that makes sense. Because then each analysis will be running parallel. Effectively. Yeah.
And you also be careful because if they're really large files, you run out of memory, and that also will kill. I've had that happen a few times.
Yes.
It was very sad.
Absolutely. All right. Did that help you a little bit? Okay. But it sounds like you're interested. There's interest. How many of you absolutely are not interested? It's okay. Be honest.
I'm still on the fence.
Okay. Okay. Well, I mean, what's time anyway? Just think of it that way. Argon is the distance between when your dissertation proposal is done and your PhD is awarded to you, particularly if you're in a simulation, right? You could be like me. I don't even have a picture of it. But in 2003, I had 4 Dell machines that I bought off the Dell outlet, like with this scrounged together money, put them down there. I only had one monitor, and I didn't even buy a switch for it. So I turned the machines backwards. I put a monitor and a keyboard and a mouse, and I just unplug and plug and try to keep track of batch files on each. And that was just by the time one done, I'd have to start over on the other and keep going, right? Right, and that was a pain, and it was extra effort. I had friends that just ran in serial, one analysis after another on a single computer. Neither of us finished quickly. You run Argon, you can run quickly. And you run quickly, you can get your PhD faster, or if you're in the tenure track or in a publish or perish place, or if you're pulling in big bucks from industry, you don't have to tell them that you ran it quickly, but you can run it quickly. There. That work? I'm trying to motivate you. Anybody flipping a little bit more interested?
I feel like I need some organizational flowcharts.
Oh, yeah, we all do.
In this scenario, do this. In this scenario, do that.
You come to learn them as you get more experience with it.
Yeah.
And generally, and this is where I was making the point last time, which is I'm not used to teaching this type of class. I know I've talked to a few of you in this sense, where I'm like, the struggle is the point, right? The flow chart often depends on sort of initial testing as to what may or may not work. Because it's hard to determine where a bottleneck might be, particularly if you're new at doing simulation research or new at doing a lot of psychometrics. It's going to be really hard to tell. So you build it in one idea, and you see, oh, nothing's going to finish because it's going to keep getting cut out. Oh, well, my options are pay tens of thousands of dollars to protect that time, or change my code. I'd change my code. So hope that helps a little bit. All right, half hour on Argon. There goes coding for today. I'm just kidding. All right, so there's another homework out. I want to hear your take on this. Have you seen it? Assignment 2, due in 2 weeks. It's a bit long, but it's repetitive. You remember your class data, your own personal data set in class. The Q matrix has standards at the top of it. You're going to calibrate IRT models for every standard, and then for certain subjects or domains. And it's going to be very regular. You're going to be estimating unidimensional IRT models and checking model fit. So if you think this sounds like a lot, it may be. You're going to be running at least 20 IRT models. How does that make you feel? A little nervous?
Nervous.
Okay. Let me give you why this is the case, though. So I worked at let's see here. So when I moved to Kansas my second time, I worked at the Dynamic Learning Mats project. It's an alternative assessment that does for states. We ended up doing diagnostic models. These are the places it works. It was built to estimate standards. And my task was to estimate basically models on every single standard. And I estimated Oh, like in a single, the very first time I did it, it was like 350, all there. And let me give you another story. Right about that same time, I was a consultant for an educational measurement company, which I should probably remain nameless, who was trying to do a similar bit of work with standards-based assessment to sell products for formative assessments. And that consulting process went to me to say to the psychometrician there, yeah, this is what you do. You got to run a model on every one. And they're like, that's just too many. I can't do that. Like, come on. Have you written a loop before? Yes. Anyway, long story short, they decided that they don't need to do that. They're going to shortcut it and run 4 models and then take subscores or based on each of those. And I had to describe to them why that's a bear. And that's actually why we have the last lecture scheduled for this class. Like, why that's a bad idea. And I believe to this day they're selling those products that are basically bullshit. So I'm just going to put it out there. So why I'm giving you this is if you'd like to work in a setting where you have to do this repetitively, there's value to that. It's important, but you have to get good at coding it to make it work. And so if this homework, the trick will be to create an analysis that does everything you want for one data file, and then to loop across to build up those data files for each of the different specs and build a loop around it. All right, so I'm challenging you coding-wise a little bit in here too, okay? Because if you can conquer that, you can do a lot of analyses all at once for a lot of different data, and a lot of what we do in the world ends up being very repetitive like that. Now, to sweeten the deal, none of this, these are unidimensional models. They'll run really quickly on your own machines, and you can use your own machines. But to tie this to Argon, I'll give you 10% extra credit. Whatever your score is, add 10% to it. If it's 100%, you get 110%. All right? If you do it in Argon. So I'm going to challenge you. Now, not all of you want the challenge, and I get that. All right? Just because this is my thing doesn't mean it's your thing. Totally understand that. That's why I'm letting Argon be optional on this one. All right? But if you want that challenge, take the challenge. I know you can do it.
You also didn't specify how we have to use Argon.
No. Well, I'll edit that. I would like you to see you do it in Argon. You can do it with one job file.
One job file.
One job file. One submission to Argon. That's how I would do it.
Okay.
Do I need to edit this right now? Here,
Yes.
let me do this. Thank you, Sergio. Hey, if anybody has a problem with how Sergio said it, thank him. By the way, I would be like that as well too if I were in your shoes. The extra credit applies only if you are able to do the analysis with the assignment, with a single job file. Better? So there's your challenge. There's lots of ways apart from that. You can test yourself on the batch file. You can just write a loop. It's not going to take a long time at the loop. These analyses are going to go very fast. Okay? Most likely you'll even be able to write a loop. Don't have to go with the, it's called an array job when you use the -T that I was showing you there with our script. You don't have to use an array job. You can just write a single file, put a loop in, it should be fine. Okay? You only need one core also, by the way, so that'll make it go faster too. It'll be assigned much faster. All right. Questions on this homework? So there's a reason for this, I promise you, right? You will find these, like, I feel like this, like I own a small business, you may know this, many of you may know this. Like, value to me, if I were to hire you, be able to do lots of analyses very quickly, right? And I think that's true of a lot of businesses when you want to go, if you want to work in industry. So I'm challenging you to get to that part with code in addition to the theory that we're trying to teach in this class as well too. All right? What's that?
My little shell script, I modified it, so I won't share it with anyone, but it does a lot of those things.
That's great, until Argon changes.
Until Argon changes.
All right.
It's not to us, it's someone else.
All right. Shall we? Any other questions before we get fired up today? Let's talk model fit. Again, this is the prerequisites section. I thought I'd put model fit here because most of you probably, where did you learn your model fit? Lisa. Wonderful. Anybody, did you cover model fit in IRT?
Yeah, some.
What do you remember from that?
Information.
Information is not model fit. Infit, outfit? Yeah, but you had that in George's class. No.
My brain's free.
Leave one out. I remember that.
That's from me.
I mean, standard error of factor scores. But
Well, that's not it either.
No.
That depends on model fit, believe it or not. If your model fit doesn't work, you have if your model doesn't fit well, your factor scores, conditional standard error is usually too small.
RMSEA likelihood ratio test.
Here we go. Here we go. Okay. What? Cast? Did I hear? Bias? Okay. We got that. We got it. It's good. So I thought I would take a little bit different track with this. This fits in with the reading I had you do as well. But I want to build model fit from the perspective of logic of why we're doing it, what makes sense. Number one, some of this absolute versus relative model fit, why model fit's important, how that fits into a multivariate models like with the Q matrix, what are the implications for validity, and something about a target distribution. So Sergio, you said RMSEA. Where does that come from?
That's a great question. That was a while ago.
That's okay. You don't need if you're sitting there struggling to think about
Square error
of approximation.
approximation.
If you learned that in the DCM class, that's bullshit too.
Okay.
Because they call it that thanks to Matthias von Devier, but that's not how it's called in SEM. It's a different statistic altogether.
Okay. So then disregard what I learned.
Okay. Okay. Yeah, I've had this battle.
I know what it stands for.
I'm dropping 4-letter words in this semester. What's it stand for? Oh,
Root squared error approximation.
correct. Why do you get it? Where does it come from? This is where I'm talking about today. Where it comes from. Now, how it's formed, once you understand where it comes from, you can form it quickly. Yeah, right?
If I'm not wrong, that's basically the difference between the model implied covariance metrics and the data covariance metrics.
Ah, good question. Good thought. But the data covariance matrix is a difficult thing
It's a
because
rated version.
that is a model.
Yes.
And this is where, and yes, that's it. You're on the right track. And that's why I'm teaching this lecture today, the logic of it. So basically, when we do model fit, the model has to look like the data. But the problem is, everything we do to the data is a model too. Right?
So is it, you take the just identified model?
No.
No, you don't.
No.
Or it's the H0, H1.
Yeah?
Yeah.
Yeah?
So the H0 is, or the H1 is not just identified?
It's saturated.
Okay.
Just identified we usually reserve for psychometric models to talk about how we identify this latent variable itself.
Oh, so it's not the model.
So technically speaking, it would still be just identified, but because it's saturated, there's no
Yeah.
other parameters that you can do. But basically, every parameter gets its own value.
Yeah.
But we're going to talk about that. And I want to build this up from the basic premise, because everything that comes from model fit falls under this category to me. So I'm trying to give you the philosophical overview of model fit, not the let's go calculate a number version of it. Because everybody can see a number, everybody can compare the numbers greater than or less than. You could probably do that back in second grade. If I told you, hey, if I got my son in here, hey Hugh, does this model fit? This number needs to be less than 0.08. Well, fractions are a problem, but I still think he'd figure that out.
Decimals.
Decimals. Oh, that's right. Fractions are not even decimals. Thank you. But point being, we can all evaluate that, but I want to give you the philosophical reason for it, right? And then to do that, I'm going to start with factor analysis, because factor analysis, estimated with marginal maximum likelihood, has a very derivable form of what we're trying to get to, right? Not only derivable, but also functional. IRT model fit's much more difficult, particularly when you start looking at categorical data. That is why the article I signed, which was, I think, a very dense article, but a very important article, existed. And then finally, we can talk a little bit about Bayesian model fit. But Bayesian model fit, if you understand the premise of why model fit exists in the first place, Bayesian model fit follows from that as well, too. We just don't have the benefit of certain asymptotic distributions we assume in non-Bayesian settings. technically, I guess we would have that benefit, but nobody really uses it that way. All right, questions? I hope, by the way, this is a different take on model fit that you've seen before, that's related to what you've seen before, but what you've seen before, particularly in Lisa's class, is subsumed into this. Meaning, in Lisa's class, you remember RMSEA, CFI, TLI, standardized root mean squared residual, and then if you really want that, go to use like something like from SAS. I don't know how many of you use SAS. I know Ahmed, you use SAS. Proc-Calis has a model fit, like it came out in the 80s when model fit was really a big deal in like the SCM world, and there's like 85 fit indices in it, right? There's all sorts of them, right? But they all sort of emanate from the same place. The logic of model fit is this: it's determining whether the model is consistent with the data or whether one model should be preferred to another, right? That's two different versions of fit, right? Determining whether a model is consistent with data is what we would call absolute fit. Meaning, I have a bunch of data, I estimated the model from that data. Does that model somehow mirror what's in the data? Right? And that seems like a weird concept, but think of it this way. How many times have you estimated an IRT model, got a bunch of thetas, and said, hey, does this theta look like the data? No, of course not. If I could observe theta, I just use it, right? So how do we determine it looks like the data is the first part. For the second part of this overall sentence at the top, the second part of it, whether one model is preferable to another, is what falls under the hat of relative fit. All right? Is my Roche model preferable to my 3PL? Right? That's a relative model fit question. The note that I really want to emphasize, though, is that in relative model fit, to really compare competing models, each one of them has to fit the data absolutely. In fact, many of the fit statistics that we use, like to compare relative model fit, and I heard someone say AIC, that's a relative model fit information criteria is a relative model fit index. But you can show that that's also incorrect if the model doesn't fit the data absolutely. Right? One of the regularity conditions for using the model chi-square, which goes into the log likelihood, which is related to chi-square, is effectively model fit. Not so many words, but that's basically it. So, questions, thoughts? Okay. So why model fit is important? Oh, by the way, that reminds me. Do I have icon up? I don't. The last question on icon, by the way, is to get you to go see if anybody's reporting model fit in their state assessments. I'm going to have you go out, find a technical manual for a state assessment, because they're posted online somewhere. Pick a state, find a technical manual, and start looking at model fit in the technical manual and see what's reported. I'm interested to see how that works. I'll share that with the group, what you find. All right. I did not say everybody has to pick a different state, so technically you could probably all pick Iowa and whatever, not to get the variation, but I hope that maybe you'll try a few different states and see what you can find. But anyway. So, if the model doesn't fit the data, is that bad? Yeah. Like you're living in dream world, right? Yeah, I could fit any dumb model I want to data. Then I could sell you the model and make you think, oh, I've got all this information, but if it doesn't appear to fit the data, whatever inferences I'm making are likely to be incorrect, maybe completely incorrect, maybe a little bit incorrect. It all depends, right? What I think about that from a more technical point of view is our parameter estimates may be biased, right? You think your factor loading's 2, it really should be 1. Think your item difficulty is 0.3, it probably was -2. Maybe that's a big difference. I don't know. Any standard error that you use, if you're in a frequentist framework, or posterior standard deviation in a Bayesian sense, will also be biased. So you think you may have much more certainty about your analysis than you really do. It's really bad, right? What's the saying? Under promise and over deliver. That's the reverse. Model fit is like over promising, right? Overly confident and wrong. Well, that describes me. But that being said, don't be me. There you go. Now I sound like my father. Do as I do, say, not as I do. All right, Dad, got it. Inferences from the model may be wrong, and here the last one's very interesting. I think the scores can be wrong, but you'll see not a lot of research on score-based, because model fit tends to be in the realm of more structural equation modeling, which stays away from educational measurement. And in that scenario, most people are worried about parameters that aren't person parameters. They're looking at structural models. They're looking at whether or not how many dimensions fit the data, but they're not looking at people's point estimates of their factor scores. In educational measurement, that's everything, and I think that's a problem. So if anybody's looking for research to work on, I'd love to start seeing how that fits. I'm sure people have looked at it before. I just have not been satisfied with any paper I've read about what it is. That's so. So once you estimate a psychometric model, that was last week's class, the first step is model fit. Because if your model doesn't fit the data, stop there, right? It's a problem. But that being said, not all good fitting models are useful. All right, I'm going to get to that in just a bit. I'll show you a very concrete example. But one model that will almost always fit is, let's imagine we're going to start with CFA, confirmatory factor analysis. Imagine a confirmatory factor analysis where all factor loadings are 0. Right? It's a pretty bad model. You have no story. That means that none of your items measure a latent variable. It means you don't have a latent variable, right? That model, if you were to generate data from it, would fit almost perfectly. Bless you. So model fit, I'd say, is necessary but not sufficient for talking about your model. But there may not be anything important in your model at that point. Any thoughts or questions on that? While I'm doing this, I want to make sure I'm recording. Yeah, I am. Hey, what do you know? Okay. All right. So, if you think about the Q matrix is a hypothesis you place about the structure of your data. Right? The Q matrix governs which latent variables are measured by which items. Technically, this is like a null hypothesis. Right? The alternative hypothesis would be that the model or the Q matrix is incorrect. So Q matrix, our Q matrix, in the process of doing multidimensional modeling from the predominant standpoint to me, which is the confirmatory setting, meaning I intend to measure these specific traits. Model fit is imperative to determine whether or not that Q matrix works well. And technically, the alternative hypothesis is a saturated model, and that's the key. What's a saturated model? And why is it saturated? That type of thing. All right, questions? How's the pace? I feel like I've been a little fast the last couple of weeks. Today, we may not have time. I was like, I'm going to fold in the coding into the slides, but we may not have time for the coding, but we'll see. We'll see. It's good because I forgot to post the coding, and I'll just have to recreate it, but we'll figure it out. Here's another argument, I think, that needs to show up, is that model fit is your first step in a validity argument. Right? Many of you have talked about validity before, seen validity before. The problem I always have with validity is it starts with the score. Thank you, bless you, bless you. If you look at a lot, not everything, not all validity, and there's certainly good papers out there that sort of represent this. But if you look at arguments like the modern take on validity, like the argument-based versions of validity, where you're building an argument as to why your assessment is valid for what it purports to do, almost all of those papers start with, hey, you have a test score. Well, damn it, how'd you get your test score? Right? I can go down the street and sell you a test score. Is that going to be valid? No. But that's like, if you get ChatGPT to run your model for you, I'm guessing it's not going to be a whole lot very valid, right? No offense to ChatGPT. You know what I'm saying, right? Think of that like the absurd, but that sort of proves the point. Like, if the score could be wrong because your model is wrong, and you don't check that your model is wrong, the whole rest of validity sort of sucks at that point. I don't care what validity has to say. Your model is wrong, your score is wrong, therefore it's not a score that you should use. So to me, I think the model fit is the first step in your validity argument. I don't like the standards. I don't like how they write about validity. They barely even touch on. There is a section of the standards that talks about model fit that doesn't prescribe methods for evaluating it, and doesn't link it to validity as well too. But I do think it belongs there. A colleague of mine that used to work at KU, he's now at DRC, Data Recognition Corporation. Is that it? Yes.
Grabsky?
Billy, yeah. He and I were like, oh, it's like consequential. Like this is important validity. It's not like argument based. This is like legitimate. Hey, my model doesn't fit the data. These aren't valid. That inferences. That's sort of how we try to name it. But anyway, all right. So the key to understanding model fit. Sorry, any questions or commentary on that? That's a bold take. Yeah.
It's the same in cognitive assessment too, but then you look at like assessments like the Rorschach, and they talk a ton about validity, so make it make sense.
Yeah, no, it's like validity, the concept of validity predates the concept of model fit. You think about where validity started historically. Like, where are the first, I don't know about you, let's just go through our history, my own memory, right? Validity, by the way, is something that, like, you may find argon boring. I read validity papers and I'm like, oh, God. Anyway, that's a knock on me. I'm trying to insult myself, right? We all have our own thing. But the primary papers I remember of validity are 1950s. Like, was it the multi-trait, multi-method matrix, Campbell and Fisk, Campbell and Stanley, something along those lines. The different types, convergent, divergent, like different ways of thinking of validity throughout the time. But then think about what psychometrics looked like at that time also, right? We didn't have computers. We had multidimensional factor models that people were not using for scores. People were doing a lot of classical theory where you're adding up data. There's no model fit whatsoever there. People will argue if you call it a model in the first place. First of all, it implies a model. So yes, it is model based. But people even argue about that, right? Anybody taken theory and technique? Did you talk about model fit in theory and technique? Those of you who took it before? No. Anyway, point being, the argument I'm going to try to make is that concepts of validity originated before concepts of model fit. And so I think that's part of the reason why the train left the station, like, you know, that saying. But I think that's part of it. I think model fit's critically important. Anyway. All right. Any other thoughts or questions? Anybody want to challenge that? I'm saying a lot of opinion here.
Well, I don't like to start with, because in my mind, validity argument should start with your construct definition.
That's good. Okay, I'm fair with that. Fair with that.
But I like adding model fit to consequential.
Yeah. Well, I mean, you have to know what you're measuring.
Right.
You set out to measure something. I sort of
And
assumed that when you built your Q
item
matrix.
development, yeah, those things are all part of validity. I think those are.
I agree.
Building of the test.
Okay, so
comes
maybe
before the model,
maybe
so.
fair enough. Well, building of the test, yes, but
Or items.
that's part of the reason I have an issue with validity in the first place, right? What's the counter to it? Are you going to build a test at random to measure random things, right? Like it's sort of.
But there's good practice.
It's sort of like saying, yeah, we're valid because look at our process. But then what if the process falls off when it meets the data? So that's sort of like I would argue. Actually, I'll make that argument. Like that's not validity. That's good construction. That helps. That may help in validity because you need that. You need good construction also. But I'd also argue.
Well, I think it's just a different view. I view validity arguments as telling the story of how the test connects. So in my mind, you start a story at the beginning. You're creating the test. You did that well.
Fair.
That's validity. Then we move on to what you're doing with those numbers.
Okay. I'll disagree with that. I'd say that it seems like it's like a post hoc excuse to say that a score matters because you thought it would matter. I'd say the construction part is you thinking it will matter.
Well, I'm not talking about whether the score matters. I'm saying whether the score connects.
Represents what you
to
think
the
it does. Excuse me.
construct.
And so it seems to me like sort of tautological, right? Like I have a score. Does it connect to the construct? Is what we're asking with validity. But how did I get the score? Well, I had to have the construct first. So therefore, to say that the score relates to the construct because I thought of the construct before I got the score seems circular. That's the argument I have with it, right? Then everything is valid because I thought it out first. Is really what the end point of that is.
Well, it's more than building.
I like this, by the way. This is a great discussion.
Well,
And I'm not attacking you personally as a human being. I'm just giving you like the PhD. Whenever I argue with other people about validity, this is the first thing I say. So you're telling me that because you established a good process to write items, the scores that come out measure the thing that you were writing? Is that correct?
I'm not saying that's the end of it.
No.
The end of validity.
No.
What I'm saying is that there are people who write items without knowing anything about how to write a good item.
I agree with that.
So if you don't have that, then you have an invalid test as well. So
Yes, I actually say that would get caught in model fit too.
right. Well, that's what you have to prove to me.
Okay, fair enough. I was trying to establish there's a circularity in the reasoning there, that my test is valid because I created the test, is sort of what that sort of shortcuts to me. Anyway.
I don't see it, but
Yes, sir.
I think the first thing that comes to mind for me when you talk about that is if I'm doing, say, like a multiple linear regression,
Mm-hmm.
I can throw in as many variables as I want. The model fit is going to improve up to a limit, but that doesn't make my model valid.
True.
So I think at some point you do have to start with this. I propose these categories, or I propose these traits based off of this logic.
Basically, I was saying this: model fit is not sufficient
Okay.
for validity. So I think that's where I'd cover that. It's necessary. You got to check the model fit. And actually, linear regression is bad at it because it actually always fits from a statistical point of view. But you can overfit. That might be the problem. But I would say this, that just because it fits may not mean it's valid. And yes, that's where I would turn to those other things as well. How is it constructed? What does it tend to do? How do these relate to other measures of importance? Those types of things. What else am I missing on your validity arguments?
How do you feel about, I can't think of what it is, what's called M+, but looking at the residual covariance matrix?
We'll get there.
Okay.
We'll get there. Get there. Because to have a residual, it means you had one in the first place.
Yeah.
And that falls under what I'm calling a target distribution.
Is that target in
Meaning,
land?
what is your, not target like what just opened on, what was that, Washington Street? Like, you know, the downtown Target, which is way better than the CVS, right? Those of you in Iowa City, it's on YouTube, but yeah.
Is it targeting in joint distribution? Are they?
We're going to get there, yeah. So I'm using it target here. Target distribution means different things in different contexts.
Yeah.
I'm using it here for model fit because model fit to what is usually the question, all right? And to me, and actually this comes up good. Vladimir, you inadvertently said this in the beginning of class, but it was really important. How well does it fit characteristics of the data or covariances or whatever? I think something along those lines, right? And that's, what did you say exactly? Do you remember?
The model implied covariance?
Model implied covariance matrix, yeah, versus, what was the other?
The saturated version.
Okay, but you didn't say that first. You said something different first.
The observed.
The observed, that's right, that's right. So what's observed in our data versus what's not is the question. And that's what I'm using it for. The target distribution is something that resembles our data. And believe it or not, actually in CFA, some of the fit statistics, the target is the saturated distribution. But some of it is not. Some of it is improvement over a ridiculous distribution. And that ridiculous distribution is the target. Then, like CFI and TLI talk about how much better your fit improves compared to independent, like a distribution as independent variables, items, and so forth. So Nathan, getting back to it, the target distribution, I use that word to be a little bit fuzzy because it may differ from different place. And not only that, depending on what your model is, what data go into it, your target distribution will shift, right? There is not a really easy way to think of what a covariance matrix might look like in certain types of data. For instance, I have continuous items and I have discrete items. What's the target distribution? I don't know, right? What's that?
There was a distribution where it's a mixture of discrete and continuous.
That's it.
That's a different discussion.
Different altogether. All right, so the target distribution is the distribution of the data that the model is trying to reproduce, sort of where the model is subsumed under. In marginal maximum likelihood methods, I'd say the target distribution of the data that would be obtained is the distribution of the data that would be obtained if the model were correct. In Bayesian models, it's the posterior predictive distribution. What's the distribution of again? It's the data, right? It's not the factor. It's not the item response function. It's the data, right? So if you collect a bunch of data, what's their distribution? Good God, it could be anything, right? So we're going to start to narrow it down a little bit, because really what it turns out to be is, let's be real, the normal distribution. Who doesn't love a good normal distribution? Am I right? Especially a multivariate normal. It looks like a Taco Bell. Like if you get the right covariance in 3 dimensions, yeah, fourth meal. Never mind. Anyway, that helped me with my dissertation. Don't try it though. The distribution itself, there's nothing that's normal. There's nothing exactly like that. So really what we talk about by target distribution is sort of what distribution gets as close to what the data should look like when we use this type of model. And I'll show that in just a bit. It's a little bit weird. But not all models have easily identified versions of this. Yeah, Cass.
I was recently reading a paper that was talking about shifting from a normal distribution to skewed.
Mm-hmm.
And they spoke about then using semi-parametrics.
Yeah.
Can you kind of just quickly give a brief on parametric?
Okay. That means, sorry, this is funny because I didn't realize this coming out of grad school. That means something to it's like a Rorschach test in of itself. If you talk to a mathematical statistician, a parametric model is something that has parameters. That's where parametric, that's the sort of derivation of that, right? As opposed to non-parametric, which might not have parameters. Often, though, those non-parametric models have parameters, so it's just sort of a distinction. So when someone will say that, oftentimes some type of discrete parameterization gets lumped into non or semi-parametric. So if a skewed distribution, if you remember, I think I showed you this in our working together, but I'm going to show this now. But 1889 was a great year. I think it was. Pearson had come up with a mixture model, Carl Pearson. This is Pearson's crabs, of course. What a great... There's a place I'm not even going to walk down. I'm just going to leave this without commentary. But he had measured certain quantities of crabs. This is a skewed distribution. He envisioned it being 2 components. There were 2 species of crabs, perhaps. And that's what he tried to estimate. This is what we would call a mixture model. We'll talk a little bit about these later in class. That mixture model sometimes gets called semi-parametric because it's a discrete process of mixing. And I think that's where the distinction I'm going to make for you happens to lie. There will be others who will absolutely disagree with that distinction. But here, you can even see it. Here's a skewed distribution. If I fit 2 symmetric distributions to it, I may reproduce that data. This, some people might call a semi-parametric process. Or thinking of it this way, if I don't exactly know what this shape is, if I go and make it a set of discrete shapes instead, I can approximate it. It's those discrete shapes that do the approximation. You can think about it also like with a histogram. Like if we're building a histogram to mirror the green line, we have to figure out a bin width, and then we have to figure out the height based on some averaging process. That averaging process would be the semi-parametric.
Sounds like calculus.
Well, we'll get to the calculus.
So then to follow up with that, could we do a relative fit between the 2?
Well, that's hard.
Okay.
It depends. Yes, the answer is yes. It may not have a satisfactory result in that a lot of our indices are driven by hypothesis testing and so forth. There is a distinction that a lot of hypothesis testing on model fit comes from log likelihoods. And log likelihoods, the scale of it depends on the distributions of the variables subsumed by them. And so if you had a normal distribution fit to this and you compared it with a different normal distribution, maybe a different mean, different variance, those are comparable, they're the same family. When you start mixing distributions and comparing that with a different family, it becomes a lot harder. There are people who've tried. There's a econometrist, I think Wong is the name. There's the Wong test to determine different distributions and so forth. It sort of rescales a likelihood, if I'm not mistaken, but it's harder. What I will tell you though is, if your data are the blue, you want, that's sort of your target, like the target distribution. The green would be some prediction from the model. And in this case, you can always quantify how far off you happen to be from it. Now, whether that fits absolutely, there's no definitive standard for it. I guess 0, like how far off you, if you're 0 away from where the blue is, you're fine, but that's hard to find too. Thanks for the question though.
Thank you.
Does that answer?
Yeah, that did.
I try to give you too much information when you ask questions, but you know.
Model fit or improvement?
What do you guys learn about model fit? Pearson's crabs. That's what you're going to remember from this class.
In our finals.
Oh, there you go. What's the most memorable? Actually, that might be a final question now because of you. Let's see if I can undo this by the end of the semester. How does that sound? All right, let's take a model and build the target distribution. That's what I really wanted to do. And this is why we're going to start with CFA. This is the model that was on my previous slide. It's for a single item. This is a confirmatory factor analysis. How you can tell that is you have an item intercept. Remember what this term in the middle was? This takes our Q matrix, and if this item measures that dimension, the Q will be a 1, so you get the loading times the factor for that dimension. If it's not, it will be a 0, right? So it doesn't apply, right? So you've got a series of factors and so forth, and then we have our error term. The error term has, for the item, a unique variance, and it's said to follow a normal distribution. That's key. How are we doing? Remember this?
I don't know if it's too off the beaten trail, but I've seen, it was in the diagnostic models a lot, exponentiating the Q matrix so that, no, don't do that. Okay.
In my opinion, those who are a lot of people in the diagnostic model world haven't experienced a lot of the other part of measurement and psychometrics, and you see a lot of weird stuff there.
Yeah.
That if you've sat in the world for a while and sat in both worlds, you can translate. But a lot of what they do is like, what are you doing? And I get it, because I was part of that before too. I still am a little bit, but you know, yeah, we are using the Q matrix to turn on or turn off that part right there, right? If it's 0, then we don't even estimate that loading, and that item contributes nothing to it. Okay?
Makes sense.
All right, that's one item, but to get to the target distribution, we actually need many, and that's where the key is. We have a whole set of capital I items like this. Now you have to remember, this is a case where every item we're going to say follows the CFA model. The Q matrix may be different. The factor pattern matrix, or Q matrix, synonyms, may be different from model to model. But what is the same? Model form, right? Thetas are normally distributed. In fact, multivariate normally distributed. Error is normally distributed, right? So this only applies to that example that, like if you're in like CFA world, like in Lisa's SCM class, right? And you're like, oh, I'm going to run a factor analysis. Everything is normal, right? Not everything's normal, but we're going to pretend anyway. That's where this distinction falls, okay? So now, a couple things. Number one, this is a multivariate model, right? Simultaneous equations, right? We have capital I equations describing our data. So let's put all these things in matrices. Shall we? I hear yay. Did someone say yay? Thank you, Lexi.
You're welcome.
Thank you. I need more applause for random stuff like that. Next time I integral, I want to see the wave. Ole, let's go. You know the wave in like sporting events, right?
Yeah.
Oh yeah. You know what I'm talking about. Okay. So here, if I take all of the item intercepts and put them in a column vector, I get mu right there, okay? Now this other part, capital lambda sub q, that's my distinction that this is a number of items by number of factors or latent variables matrix, such that the entries are either 0 if the q matrix is 0, or the lambda parameter for that specific item and factor if the Q matrix is 1. Right? It's like a superimposing element-wise multiplication of all the lambdas and all the Q. I'm just combining it into one for it. You want me to draw that? You want to see a visual of it? Would that help? Okay.
I don't know what you mean by.
Siri.
Siri, I see a visual of it with the help.
Hey,
How about a web search for it?
how about not? Love it. That was perfect timing too. Okay. I'm calling this lambda. And I put a little half arrow over my vectors and matrices that I draw because you can't see boldface. So that's what this is. Lambda sub q equals, and let's imagine for a second my Q matrix look like this. Can we just have 3 items? Would that be okay? 1, 0, 0, 1, 1, 1. Okay? So now if I were to superimpose all, so if you think of it, if all I had was 1s in the Q matrix, first of all, it wouldn't be identified. But second, I'd have all the lambdas here, right? But here this is saying, no. I have lambda 1, 1 here. I have a 0 there because that's a 0 in our Q matrix. I have a 0 here. I have lambda 2, 2 here. And then I have lambda 3, 1 and lambda 3, 2. All right, so this is what we would actually call a factor pattern matrix, right? It has the pattern of zeros where the items don't measure the factor, and loadings where they do. That's sort of the difference between the Q matrix and the factor pattern matrix. Does that help? Okay. What's that? What did I do?
1 second.
1 second.
Sorry.
No
I'm so
problem.
sorry.
No, while we're there. Other questions on it, right? So while we're here, I should also put mu, that vector was just for 3 items, mu1, mu2, mu3. Okay? Okay. All right, next. Where did it go? Where did it go? There it is. My next is my theta, right there. Theta matrix, right? So here, theta is a d by 1 vector of latent variable scores for a person. So what do I mean by that? Let's build theta here. Theta for a person. There are 2 dimensions, right? So this is theta person 1 and theta person 2. So person P is the person. Okay? All right. So remember matrix algebra?
Yeah.
Yeah. Of course. Well, I'm going to make you multiply. Like what's happening when I multiply theta by Q is that this first row multiplies the 2 thetas, right? The second row then multiplies the 2 thetas, and the third row multiplies the 2 thetas. So this 3 by 2 multiplied by a 2 by 1 gives me a 3 by 1 output. And what ends up forming then is these scalar equations. It's the Q times theta is the middle portion of the scalar equations right there.
Wouldn't it technically be the transpose of that?
No, I don't think so.
I mean the transpose of the Q, lambda Q matrix.
Did I do the math wrong? 3 times 2 by times a 2 by 1. No, I think I got it right. I think I got my dimensions right on this. So here's why I say that. I always talk about the size, right? The size of the matrix determines whether you can multiply it. So
Yeah.
3 by 2 times a 2 by 1 will lead to a 3 by 1. And then the other flip to that is, in matrix form, this is a 3. There would be 3 items right here. So there'd be 1 entry, 2 entry, 3 entry right here.
Can you go back to the matrices real quick?
This one or the other one? Hmm?
Yeah, the theta p matrices, wouldn't it be like theta of latent 1, theta of latent 2? Like why is it people there and not the different?
Oh, okay, yes, that is exactly it. So theta, it's item by dimension here, right? So did I change my notation here? Yeah, that's it. So here, each item by dimension there. So when I look at theta here, this is the first item, the first dimension is what that's saying.
I was looking at theta.
Oh, theta.
P1 and P2.
Yeah, I'm just showing a single person here.
So the P doesn't stand for person. Like
P
it's
is a hypothetical
matrix of
individual.
All of the.
Yeah, that's just a single person's data.
Okay.
That's how I'm showing it here. If I didn't have that, then I'd need a transpose. I'd need some other function to be able to do it. That's why I left it with P. So I could, basically I'm trying to connect this. Whenever we just talk about factor analysis, we show a bunch of scalar equations. And it's usually that scalar is for a single person, right? So I'm trying to build that into the analysis as well. Yeah.
So your lambda q is I times d, not d times I.
Correct. Thank you.
Okay.
I'll fix that. I fixed the slides last week, but I will fix that. Slide 10. I'm going to make a note of me. All right. Thank you. Good catch. Other questions? All right. Next then, theta follows a multivariate normal distribution. Right? So these are the factors. We don't observe them, but we have to give them a distribution. We usually have to. We have to figure out what their moments are to identify it. So in this case, theta itself, if we say theta for a person follows a normal distribution, I like to denote the number of dimensions it is just by putting it below the n. Doesn't always get denoted that way. But here there's a mu for a theta. Whoops. Jeez. Come on, Templin. And here, these are matrices. So what does that mean? Mu for theta is just a mean vector, right? This is mu for theta 1, mu for theta 2. More often than not, usually, I'll put that, oh my God, I can't even spell. Usually, I don't know what the mathematical symbol for usually is.
Approximately, maybe, the two squiggles?
That's only this is not approximate, this is exact
It wouldn't.
in a usual sense.
It would just be conditional. Just-
But usually this is a bunch of zeros, which we often denote as the zero vector, right? Because when we identify, did I get that right?
The same way, I mean, like converting v with dash
Oh, is that
for every.
yeah, but that's not it either, because in a measurement model, if we're doing like a calibration, we want these we usually put these at 0 just for identification, so we don't often think about it. There are certain instances of psychometric models where we don't. Some of those include measurement variance. Some of those include structural models where you want to make predictions about certain things, or if the theta is being predicted itself. So in many times, for what you see in this program, these are almost always a 0 vector, unless you were in the latter half of Lisa's SCM class. How am I doing? Those of you who've done all this before, how's it going, Alfonso?
How about set? I use set.
Set. S-E-T?
Set equal to 0.
Set equal to. Yeah, that's it. I would say that. I was more like, yes, usually we do set them equal to 0 by definition, right? So I guess that's usually that, maybe. 3 equals is defined as? I don't know. Anyway. What?
I think so.
Yeah. But it's not exclusive, and it's funny because the time, like if you're like me as a grad student when I was learning this and I was already overwhelmed by everything else, I'm like, when am I going to have to know that? Yeah. And then it hits you right in the face 2 weeks after, you're like, I'm not going to need to know that. Oh, hey, I got a project. I need you to do this with the theta mean. God, no. Anyway, it happened to me all the time. I'm just trying to leave a little bit of room, kind of like when you go to the coffee shop and like, you want room for creamer? Just leave a little bit of room for that. That's all, right? Most of the coffee is still the coffee, but you may want to add a little theta mean to it or something like that. It almost sounds, never mind. All right. Phi, this is a capital phi, P-H-I. Uh-oh, yeah.
So if we're writing the distributions for an individual person's theta in this manner, are we assuming that they're completely uncorrelated?
With other people, yes.
Well,
No, sorry, the thetas themselves. I haven't gotten there yet.
I meant per person.
So the two thetas
Like
themselves.
A multivariate distribution rather than.
This is a multivariate normal. And so I'm just about to get to where that goes. So here, this is a mean vector. This other term, phi, is the covariance matrix. Okay, so phi, this thing will be 2 by 2, or number of dimensions by number of dimensions. The diagonal of it, right here, the diagonal, this thing right here, are the variance of the factor. In the off diagonal, it's the covariance. Now, before I get to the final part of that question, I'm going to do my usually, and I'll put this in quotes because this is actually more fluid in our program than the mean side is. But usually what this equals is this. The factor variances are fixed to 1 per estimation. The covariance is estimated, and in the case where you have a covariance matrix where the diagonals are 1, that is actually called a correlation matrix. Identity is where the diagonals are 1 but 0 otherwise. So, I mean, technically this needs to be positive semi-definite to be a positive correlation matrix. You know what positive semi-definite means?
Yeah, wish her.
No. What I mean by that is if we do the mathematical determinant, and those of you who don't determine it, has to be greater than or equal to 0. It's positive semi-definite. Why it needs to do that is if you look at the distribution function for the multivariate normal, got to invert it. Right here, not only do you have to invert it, but this distribution function, that's a determinant that needs to be positive, otherwise you get a negative likelihood, which is not good, and there's an inverse as well, too. So when you assume something's multivariate normal, you're making the implicit assumption that the covariance matrix is what we call positive semi-definite. Hope I'm challenging you. Is this challenging? Okay. Am I trying to sprinkle things in that didn't show up before? That's what I'm hoping with this. Just pouring salt in the wounds, maybe. I don't know. But, so, the point is, usually that's estimated. It's just, so when you see a multivariate normal, you just assume that there's some covariance or correlation being estimated. That's the association between the factors. Cool? Other questions on that? No. Anybody want to shoot me? Actually, I thought about that. Maybe you could bring water guns? Actually, no, with the equipment. Not good. But there's got to be Nerf guns. If you, I will encourage you this. If you bring a Nerf gun to class and shoot at me when you don't understand something, I would love it.
We get extra credit?
Yeah, I might make it that way. Anybody?
Candy bags.
How many of you have Nerf guns?
I can buy one.
Oh.
Like $5.
Well, you don't need to buy it. I don't want you to spend your money on Nerf guns because I said so in class. But yeah, seriously, a Nerf gun. But here's the thing: if you shoot at me when you get it wrong, I'm bringing my own. I'm going to pack it, and you're not even going to know, because I think I can concealed carry these things, right? Anyway, what is this all about? No, we're going to have some fun. Anyway, so we're almost through with this. Okay, one last one, then it's break time. The last matrix to worry about is error. So error follows a normal distribution. Always, without exception, there's a 0 mean. If that mean wasn't 0, it turns out these other parameters get a nasty bias to them. Because now you're saying that that mean that you give to error needs to be removed from some other part of the model. Usually it's the intercept it goes away from, but some other parameters that may go as well. So always the 0 matrix vector is the mean of error. Now remember, error, every item has it. And we have 10 items. Or actually, in the example I'm drawing right here, I don't know why I'm seeing things. Your simulation has 10. But error here, the person, this is a 3-item example that I'm showing here, right? By the way, this is not even identified with 2 factors, but anyway, for 3 items, this is like saying error person 1, error person 2, error person 3 is the items. But moreover, if I were to look at error for a person, follows a normal distribution with capital I items. This other matrix right here, that one, psi, that term is our error covariance matrix. Right, so psi look like this. It's number of items times number of items. So now I'm backing away from our 3-item example, mainly because 3 items in 2 dimensions is not identified. But if I did this, then I would get lowercase psi 1 1 squared 2 2 all the way down to psi I squared. And here comes the interesting question. If you believe in psychometrics, we like to say items are independent conditional on the latent variable. We call that conditional independence, sometimes local independence. You've heard of that term before? Yes. In factor analysis, that is explicated by putting zeros in the off diagonals. But it's not necessary because you can actually estimate that. You can actually violate that assumption in factor analysis. Not a good idea. It weakens your validity argument. Because if you say that two items are correlated after you explain the item, the factor, after you explain them with the factor, that really means you're measuring the factor and other things. So every time I see that, I'm like, oh, look, I measured openness to experience, but I had to add a residual covariance. And really, your openness experience is openness to experience plus other stuff. Right? That's what it means. Unexplained. So that's this matrix. Questions on this? I know you're not going to ask questions as much on this one. It's break time. All right. Should we take a break? Okay. 10 minutes. Pause in the action. Come back and enjoy some more.